We'll have a look at example 5. This vessel has a fire. It's a ro-ro vessel, and we put the trencher system into operation, and there's block scuppers on the deck. So the deck becomes flooded, and it's flooded to a depth of 0.5 of a metre, and we're given the dimensions of our deck, 100 metres long and 20 metres wide. There's our displacement, kg, km, height of the vehicle deck above the keel, 9.75 metres. Calculate the resultant GM, and let's have a look at the result. So, first thing to note is that the, if you like, the weight of the water, we need to work that out, is 100 times 20 times 0.5, length times breadth times depth of water, of course multiplied by density to give weight. So we've got 1025 tonnes on board. The free surface moment created, lb cubed over 12 times density, 100 times 20 cubed over 12 times density gives us 68,333 tonne-meters. So that's the free surface effect, or the free surface moment I should say, the free surface moment lb cubed over 12. The free surface effect is going to be the free surface moment divided by the weight. Now this is where you don't use the initial displacement. You have to use the displacement plus the water that's come on board, 21025. So it gives a free surface effect of 3.25 metres. So let's work out our kg of the vessel, having had this water come onto the vessel. Initial displacement, initial kg, weight of the water. Now the kg of the water, kg means a measurement from the keel to the centre of gravity. So our vessel's centre of gravity is 8 metres above the keel. The centre of gravity of the water is going to be the height of the vehicle deck above the keel, 9.75, plus the centre of the depth of water. Now the centre of the depth has got to be just half its depth, which is 0.25. So our kg is going to be 9.75 plus 0.25, making 10. Work out the total moments, divide by the total weight, and it gives us a kg of 8.1. Our km, we're going to just assume it's constant. In later problems you'll need to look in the hydrostatic particulars. We're assuming it's constant. Gives us a solid GM of 1.9. Free surface effect reduces our value, therefore we've got a fluid GM of minus 1.35. So we can see that initially we had a reasonable GM of 2 metres, but as a result of the free surface we've now got minus 1.35 as our fluid GM, and that's how serious it can affect the vessel. Now let's have a quick look at if we have a subdivision. When we talk about subdivisions, we're reducing the free surface effect, and we reduce it by 1 over n squared, where n is the number of tanks created by equal subdivisions. So in other words, here's our original tank and our original free surface moment. Let's introduce one division there. We've got 2 compartments, therefore it becomes 1 over 2 squared. So that was 1 over 1 squared, 1 over 2 squared. So the free surface moment, free surface effect, is only a quarter of what it was previously. If we have 3, it becomes 1 over 3 squared. So in other words, the free surface moment has now been reduced to a 1/9 of what it was. So if we applied this to the previous example, we had 68,333 tonne-meters for our free surface moment. Let's put one subdivision in, and we can see that it's reduced immediately to 17,083 tonne-meters. Divide that by our displacement, and our free surface effect, or free surface correction, is now 0.81. Our solid GM was 1.9. Instead of the minus 3.25, it's minus 0.81. Fluid GM is going to be 1.09 of a metre. So now, by just introducing that subdivision, you can see that we've regained positive stability. So introducing divisions in tanks has a almost a disproportionate effect. It considerably reduces the free surface, and if you can say that the free surface really is inversely proportional to 1 over n squared, where n is the number of tanks created or number of compartments or tanks that we create by introducing the subdivision.